In this video, we're going to talk about the consequences of measurement error in both the dependent and the independent variables in a regression. If measurement error shows up on the left-hand side of the equation in the dependent variable, the consequences turn out to be relatively minor. It essentially means that we just have more randomness in the equation, that we have more noise in the error terms. As a result, we end up with a larger variance for the error term and higher standard errors because of that for all of our estimated model parameters. And in consequence, we end up with somewhat lower t statistics and a lower r-squared than we might have received if measurement error had not been present. However, there's generally not too much we can do with this, simply because if we had a good measure of our dependent variable, we would be using that instead. So there's really not much we can do to correct for it, but fortunately, we still end up with unbiased and consistent estimates of all the model parameters, as long as the measurement error is independent of the error term in the underlying population regression equation. Measurement error in an independent variable, though, is a substantially more serious problem. The consequence of it is that it results in estimates of model parameters, of slope parameters, that typically are downward biased. This diagram should help illustrate that. Suppose we just start at the sample mean of x. Let's suppose we measure x with error, and we observe a level of x that's above the mean because of a positive error term. In that case, our data points would tend to be below the regression line because the actual x is overstating the true value. Similarly, if the observed x, the value of x measured with error, is below that true value, we end up with observed points that are above the regression line. So when measurement error is present, we tend to end up with an estimate of the slope parameter with respect to that variable that tends to have a downward bias, as in this example. The solution that we normally recommend when possible is to use something called an instrumental variables estimator. The procedure that we use is we try to find one or more variables, we call them instrumental variables, that are correlated with the variable that has measurement error, but that are uncorrelated with the error term. We then take the independent variable that's measured with error, and we regress that on the set of instrumental variables, including a constant term in that regression. We save the predicted values from that regression equation, and we estimate the original equation, but we replace the variable that's measured with error with a predicted value from this first stage regression, the one we described in step 2. This results in consistent, albeit biased, estimates of all model parameters. This procedure is also called a two-stage least squares procedure because there's 2 stages to the regression. The first is to regress the variable measured with error on the instruments, the instrumental variables, and then in the second stage, we run the regression, replacing the noisy independent variable, the one that has measurement error, with the predicted value. One problem, though, in practice is it's often hard to find instruments, and that's because, in part, many of the variables that we're interested in are not directly observable. And because of that, we use what we call proxy variables. For example, if we're trying to measure someone's ability, someone's cognitive skills, or someone's physical ability, or something similar, we only have rough approximations to that measured by test scores, by tests of manual dexterity, and so forth. And similarly, if we're trying to capture the effect of expectations, we don't directly observe these, but we have observable measures that serve as rough approximations to these variables. All of these proxy variables are essentially, by their nature, subject to measurement error because they're our best approximations to the underlying variables that we don't observe. The problem basically is all of these variables are essentially subject to measurement error. We generally don't correct this in practice in these cases because any instruments that we'd be likely to use tend to have a similar sort of measurement error. The consolation, though, is that if we find significant results when we include our proxy variables, it's likely that if we were able to find a direct measure of these variables, the result would be at least as strong because of the general downward bias in these estimates, which means a significant result when measurement error is present is likely to actually understate the actual magnitude of that effect. So generally speaking, when measurement error is present, we'll report that in writing up our results, but in general, it's often not corrected because it's difficult to find very good instruments.